Now we come to the next lesson in this physics use case where we use the opportunity to discuss the binomial distribution, which is a very important concept in the theory of random or the practice of random numbers, because many things have the binomial distribution. So to get the binomial distribution, we need to think of things that are which are very simple. They only take the value 0 or 1. Historically, maybe these first came up with tossing coins. They're either heads or tails. That's effectively 0 or 1. And we've already pointed out many times that the histogram case is that type that x equals 1 can be that the particular event is in a histogram, and x equals 0 is that it is not. So 1 and 0. So if we have a probability mu, which of course the coin tossing is 0.5 for a decent coin, that a particular event lies in a bin, and of course we can generalize coin tossing that bias coins, which either preferentially become heads or tails. Then we have a random variable with two variables with probability mu that it's 1 and 1 minus mu, because probability always adds up to 1 for 0. And we can easily count the average value of x is mu, and the standard deviation is is the square root of the average value of x minus mu squared. And so the standard deviation squared is trivially calculated to be 1 minus mu into mu. From mu small, which has been the counting case we've been doing, 1 minus mu is 1. Standard deviation squared is mu, so sigma is square root of mu, which is the square root of the mean. But this is the 1 minus mu into mu is a result true whether or not mu is small. So in our case, the chance of any one event lying in any one bin is negligible. So mu is small number, then 1 minus mu is essentially 1. And so we get our usual result that the standard deviation is the square root of the average. So if we now do what we do with a histogram, which is to count the number of times we populate a particular bin, then we calculate the sum of the x's, and then this thing called O, which is then the number of points in the histogram, has a mean, which is n times mu, and a standard deviation, which is square root of n. That's because it's the sum of n events, and so we always know that we get a square root of n then when we add them up, times the standard deviation of x, which is square root of mu. So we get the fact that when we sum these binomial distributed events with small mu, that for the sum, we have a mean, which is whatever we count it up to be, and the error is the square root of the mean. And that's why we have an error of 5 when we observe 25 events or 250 events in the counting experiments we did. So this is just a recap that error is the square root of the mean for counting. This is really important. It's sort of trivial, but it's actually most important things are trivial. So this underlies everything we do. Say, and the binomial distribution is 1 for events in the bin and 0 for the events outside the bin. And let's sort of come back and get back to physics again, because we've been doing too much mathematics, and just remind ourselves how this looks for the actual data that people take. So here's, we've done all sorts of apparatus pictures. The last one I think was of Atlas. Here we have CMS. I pointed out the importance of the magnet. This is the magnet here, the solenoid, which bends the particles which are going off in this direction. And here we have these calorimeters, which are the ones that measure what happens when particles crash into them. And they have electromagnetic calorimeters, which are done very precisely. and hadron calorimeters, which are not done so precisely. And we detect muons because they hardly interact at all, and photons, which are critical. Remember, the Higgs goes to two photons; those are in those electromagnetic calorimeters. So calorimeters measure energy, magnets bend, and weakly interacting particles hardly do any interaction. So putting all this together, you find out quite a lot about what goes on. Here's our famous type of event we've seen many times, bunches of charged particles bending. Here we are, here's a particle bending. And then then we have in the photon calorimeters, those green things, we see the two photons going off. They're going off transverse to the two protons, so they're very interesting photons. This stuff that happens here is not so interesting, because these are the fast particles. They're following the protons, so typically are not interesting. So is this is the type of thing the trigger's designed to select, and the analysis is which is meant to find the Higgs boson. Now there can be background, like you could produce, I don't know, 2 pi zeros, which each pi zero itself decays into 2 photons. And so this photon here comes from one of the pi zeros, the other photon here comes from another pi zero. When the pi zeros went into photons, they did it selectively, so that one of the photons took most of the energy. So this could be actually a pretty rare event, 2 high transverse momentum pi zeros, but not interesting. That's one of that sloping background on the original thing we studied. So what are we doing here? This is the 4-lepton final state, a different final state. And we have a signal here, which is over the background here. And these are various background events. And this little red thing here is what happens when the Higgs mass is where it ought to be. Well, it's where we now know it is, 126 GeV. And this has not really got enough statistics to be absolutely robust, but it confirms the measurement because it shows an excess of events of the Higgs boson. And all this stuff here is background from various possible final states, which are of different colors. And remember, when I did phenomenology, I would try to generate these colors for you, which come from the model. When we're making models, and we take the models, see what they predict. They're not too bad. They roughly agree with the experiment. They have adjustable parameters, which are adjusted to have the right normalization. And that tells you whether you stand much chance of seeing the signal. And in this case here, there is actually a gap. If the Higgs boson had a different mass, it may be swamped by either this or this, which are not so interesting. I already pointed out signal over background. We've seen essentially this plot before. Here's the signal. And here's the background, this green thing or dash thing. The dash thing here is the background, and then they measure standard deviations from the background to show that this really is a very, very big signal. This is you use your physics intuition to select which of these plots to look at. And your physics intuition is partly what theory predicts and partly what actually the data tells you. Both of those go into your physics intuition. So this single histogram probably came out of thousands or tens of thousands of other histograms that people looked at before they found this was the way to look at it, etc. This actually is a little interesting problem with the statistics of these events. You need to be careful to use the proper statistics and say that, well, what you see is not unique. And you didn't actually know where to look. So you're actually looking at other places. So where you see a signal in 1 out of 100 plots is not as significant as if you only have one definite plot that you know you're meant to look at. So one of the important things you need to bear in mind in this type of analysis is to put in the fact that you're searching in an unbiased fashion because you don't actually know what the answer is, and therefore you're looking through lots of possibilities, and the probability of something, as everything is distributed Gaussian, so there's some probability of a pretty big swing. You have to put that into your analysis to say that there will be some. If you look at 100,000 histograms, there are going to be some pretty wild things going on in those histograms because the chance of something happening 1 in 100,000 times is quite small, and so that you can see the tail of a Gaussian in some of those histograms. You need to be pretty careful. So when you have a signal which is measured by a number of events and a background measured by a number of events, the statistical error is the square root of the sum of the signal plus the background, and you need this error here to be smaller than the signal, or I should say, of course, as it says here, much smaller than the signal. And as you always, well, nearly always will have background, that this is a much harder problem than making the square root of the signal smaller than the signal. So, I don't know, probably 50 events, or let's say 49, the square root of that is 7. That's pretty significant that there was no background. But if the background is bigger than the signal, you need, as we saw for the CMS data, you need thousands of events in the signal to distinguish it from the background. And I also mentioned already systematic errors, which are errors in the plots which come from the fact that you didn't measure things precisely, didn't interpret things quite right, and so you don't actually get a clean signal. There are errors, and those are either a model-based uncertainties or analysis or instrument-based uncertainties, and they do not decrease like the square root of the total event sample. They can be fixed or completely fake. All sorts of things can happen with systematic errors. So you need to be a very good physicist to understand what's going on from the theory and the experiment to rule out systematic errors.